Consider two lines, L1 and L2, passing through the origin as shown. Let theta be the acute angle formed between lines L1 and L2. You will learn to find the value of this angle theta using the direction ratios, direction cosines, vector equations, or Cartesian equations of the two lines. Consider a point A on line L1 and a point B on line L2. Now, consider the directed lines, OA and OB, representing the position vectors of points A and B, respectively, with respect to the origin. Let A1, B1, C1 and A2, B2, C2 be the direction ratios of lines L1 and L2 respectively. Thus vectors OA and OB can be written in component form as shown. We know that the cosine of angle theta between two vectors is given by their dot product divided by the product of their magnitudes. The dot product of vectors OA and OB is equal to the sum of the products of their corresponding components as shown here. The magnitude of vector OA is equal to under root of A1 square plus B1 square plus C1 square. Similarly, the magnitude of vector OB is equal to under root of A2 square plus B2 square plus C2 square. Substituting the values of the dot product of vectors OA and OB and their magnitudes in the expression for cos theta, we can find angle theta between lines L1 and L2 in terms of their direction ratios. Let this be equation 1. Now, we will find the sine of angle theta between vectors OA and OB. From trigonometric identities, we know that sine theta is equal to under root of 1 minus cos square theta. On simplifying, we get the expression for the sine of angle theta between lines L1 and L2. Let this be equation 2. These equations lead to some interesting observations. If lines L1 and L2 are perpendicular to each other, then the value of theta is 90 degrees and cos theta is 0. Equating the value for cos theta to 0 from equation 1, we get the condition for the perpendicularity of two lines. If lines L1 and L2 are parallel to each other, then the value of theta is 0 degrees and sine theta is 0. Equating the value for sine theta to 0 from equation 2, we get the condition for two lines to be parallel as shown here. The given lines, L1 and L2, may not always pass through the origin. In such a case, we find the angle between them by considering lines L1' and L2' that are parallel to L1 and L2 and pass through the origin. Now, let us see how we can find angle theta if we are given the direction cosines of lines L1 and L2 instead of their direction ratios. If L1, M1, N1 and L2, M2, N2 are the direction cosines of lines L1 and L2 respectively, then from equation 1, cos theta can be written as shown. Let this be equation 3. We know that the sum of the squares of the direction cosines of any line is always equal to 1. Thus, the terms in the denominator of the right-hand side in equation 3 is reduced to 1. Equation 4 gives us the equation for the cosine of angle theta between lines L1 and L2 in terms of their direction cosines. Replacing the direction ratios with direction cosines in equation 2 and simplifying, we get the equation for the sine of angle theta between lines L1 and L2 as shown here. Now, we will find the angle between the two lines when their vector equations are given. Let us represent the two lines L1 and L2 with their vector equations. Let the vector equation of line L1 be vector A1 plus lambda into vector B1. Similarly, let the vector equation of line L2 be vector A2 plus mu into vector B2. The cosine of angle theta between the two given lines is equal to the modulus of the dot product of vectors B1 and B2 divided by the product of the magnitudes of the vectors B1 and B2. Let us now find angle theta using the Cartesian equations of lines L1 and L2 shown here. From the Cartesian equations of the given lines, we get that A1, B1, C1 and A2, B2, C2 are the direction ratios of the two lines. Thus, the cosine of angle theta between the lines given in Cartesian form can be found using the formula shown.